You ready, right? Yeah.
Yep,
Okay.
sure.
Okay. And view full screen. Okay. All right. Good morning, guys. As we talked before, our first speaker,
First one?
industry speaker. Our first industry speaker for this quarter will be our friend Todd Christensen. Todd is a consulting specialist,
Consultant application engineer.
consulting application engineer with Cutler Hammer, one of the major manufacturers of electrical equipment. They do a great job in switchgear, switchboards, panels, transformers, and a bunch of other things. So Todd has a great presentation, guys, that he's going to go over. The highlights that I always think the highlights that Todd brings is the difference between switchboard, switchgear, panel boards, MCC, because these are all panels and the code almost treat them the same, but they're different from the industry point of view. So these are great. Todd also is going to mention the consulting application guide that we have here. It's also online. We can forward the link to you so you can get cut sheets and information about a lot of equipment from Cutler Hammer. So, and he has some power presentation, really nice about power distribution and so forth. Todd has been doing it for, gosh, for how many years now?
It's over 17 years.
Yeah, I mean, doing the presentation for us.
Oh, geez, yeah.
7
years?
7 years,
8 years?
8, 7 years. And I'll let you introduce Cutler Hammer and yourself.
Okay.
Thank you, Todd.
Thanks, Chad. As Chad mentioned, my name is Todd Christensen. I'm going to leave some cards up here for you as well. I'm an application engineer for Eaton Corporation. When you talk about power distribution products in the commercial construction industry, panelboards, switchboards, etc., you're really talking in North America about 4 major manufacturers. And I don't know what the market share we have is, but it's got to be well over 90%. And that's Eaton Corporation has competitors that you may probably know if you've been in the industry called Square D, General Electric, and Siemens. Eaton Corporation itself, if you look back to our history into this business, you can go back to George Westinghouse, who was digging back into the many years ago, but with Tesla inventing electricity, AC/DC, and all this argument, when they're first getting around to how do we put an electrical distribution system in a country, in a city, in a building. And George Westinghouse founded it, so that the invention of circuit breakers goes back many, many years. Kind of all the way up to in the 70s, there was a company called Cutler Hammer that was in the power distribution business, but primarily they were very light commercial, load centers, residential, and a lot of control, things that would go with motor control, some of the stuff I see on the wall here. Cutler Hammer hung around that business and was purchased by Eaton Corporation sometime in the 70s, I believe. Eaton Corporation itself was a big automotive play. If anybody dabbles in the automotive into superchargers or turbochargers, power management or air management through an engine, that was kind of Eaton's forte. That's what they did. They got into this business by buying Cutler Hammer in the 70s, and the big transformation was 1994 when Eaton Corporation purchased Westinghouse. So Westinghouse's distribution and control was probably the largest when it came to highly engineered products in the industry. In 1994, that fell under Eaton Corporation. So since 1994, we've had a pretty wide variety of companies that we've also added to our base core of power distribution. Things like UPSs. A company called PowerWare is now part of Eaton. We make generator paralleling switchgear under a company called Cat ISO, and they've pretty much expanded globally as well. So when you cross the ocean, you'll hear some other power distribution names like ABB, or a lot of OEMs into different areas. So funneling in back up to today, when you're building a light commercial, then Eaton Corporation is, especially in this market, I would say Eaton Corporation and Square D are the top two in the Twin Cities. General Electric would be pretty popular as well. Our forte for Eaton Corporation, if you think what do they do different than all the other guys, we all make the same kind of stuff, is that we have a lot of highly skilled engineers. So we lead the industry when it comes to R&D, and we're very good at tackling complicated jobs. Jobs we're talking about, or the panelboard switchboards we talked about today, I would consider those pretty straightforward. When you get up into the larger facilities like an airport, where you've got a whole, it's a city amongst itself, and industrial plants where you get some pretty heavy duty processes, that's the kind of stuff we play really good at. So what I'm going to do today, we got this whole power distribution here.
Where right on the screen.
Okay.
Yep,
Like one of these. Let's do blue. And I'm going to try this out. We didn't do this last time. But this is a whole distribution system. So it starts at the top with the generating station. So this is what Excel has around here. You've got coal power plants, you got nuclear generation, etc. They transform that, and that's anywhere from say 10 to 25 kV or kilovolts. And they transfer, they move that to a switch yard where they step it all the way up to say 800 kV. And then when they get local, back into a certain area that's going to use the power, you'll step it down into a distribution substation, typically down around 34 kV, maybe as low as 15 kV. And then from there, you start farming into your different loads. So your different loads are an industrial load, a residential load, and what we're going to talk about today with panelboard switchboards is the commercial load. And they all have their own different voltages that they use. And just in this range from I'm making power to I'm using power, you can go through 4 or 5 different voltage levels. Anybody have an idea why we need all these different voltage levels? Why would we want to get a very high voltage when we're moving it from here to here? Why do we step it up before we bring it down? Reduce loss, exactly. It makes it much more efficient to get a very high voltage to move it across the line. When you get down to the end points, you want to take it from a good transmission voltage to a usage voltage. So when we're talking commercial, we've got, it is the clear.
You can write all over it.
If I want to clear it, then
Yeah, just click on that red X.
red X.
Yeah. Maybe a couple times. There you go.
Perfect. Okay, excellent. So then when we step up to what voltages actually make sense to us? What can we use in a commercial facility? Well, UL recognizes the voltages that we can use. UL is Underwriters Laboratory, and they pretty much set the guidelines for equipment that is built in the United States. Now, UL, over the years, and probably within the last 5 years, has changed from a not-for-profit company to a for-profit company. One of the twists that is coming along with that, and we're kind of in that now, is that things like a government facility, whether it's university, they're having to open their doors and say, as a private company, we can't say you have to put UL-rated equipment in my facility. They have to kind of modify that and say you have to put a third-party, nationally recognized testing laboratory, NRTL, into mind. There's a couple of other third-party testing agencies that have been around that some are getting bigger right now. Like in Canada, they have something called CSA, Canadian Standards Association. Um, so that's kind of where we're evolving into that process now. But for the basis of what we're understanding, UL still dictates the guidelines on how we manufacture and design equipment. Everybody else who's a third party really just takes UL's guidelines and uses the same thing themselves. So these are the voltages that we have to follow. 208 120Y is very common, as well as 480Y 277. Those are two of the most common voltages you're going to see that come into a facility for power distribution. Those same voltages in the delta formation are also available. You'll see those more in a industrial type application where you don't necessarily need a neutral, or you have more three-phase loads than single-phase loads. Okay, so drilling down inside the building, for the sake of this will kind of be the guideline of the power distribution system. Coming in, you'll have a transfer here. You'll have some kind of fusible switch, and this transformer here then will step it down to your user voltage, and you can put this anywhere. This could be an owner supplied equipment inside the building or utility supplied equipment outside the building. But once you step into your distribution switchboard, that's the main board for the plant. That is the hub everything's coming out of, going down to your distribution panels, your motor control centers, smaller dry type transformers that may step this from 480/277 down to 122/08. This is the gist of the power distribution system that we look at in commercial facilities. And we'll circle back to that at a couple points later. But when it comes to a distribution system, there's two goals that we're trying to accomplish with the power distribution system. The ultimate goal is the usability, or it's the ability to distribute the power from a 3 lines, electrical lines that the utility's handing you, into the equipment that's actually using the power. So it needs to distribute it economically and safely. And economically and safely don't necessarily go hand in hand. So this is where it kind of rotates also to the engineer of record, that the consulting engineers who's putting this on paper sometimes has to look at a couple of different things there. But safety is always the most important factor in a design of any facility. And then once you cover your minimum safety requirements, then it's also a matter of economics to being able to do that in the most cost-effective manner. As we know, the economics of construction are very important, I guess, in today's industry, with all the construction pretty much in a I'll call it, we're still in the downside of commercial construction. There's a lot of contractors out there looking for work, and when more contractors are looking for business to put their men and their teams to work, that's just going to drive the price lower and lower, so you get into more cost-effective design options that actually then funnel on back up the line to the owner, the guy who's writing the check to make this whole building. Now, the second goal of a power distribution system is protection. So number one is you're distributing power. Number two is you got to offer protection for your facility. The two types of problems that you're looking to protect are overloads and short circuits. And overloads are pretty straightforward. I'm overloading my circuit. If I've got a 100 amp circuit and I go in there and I'm plugging a 120 amp load in there, nothing's going to happen immediately, but over a time period, whether that's 15 minutes, 30 minutes, 30 hours, depending on the equipment you have protecting it, that will trip that circuit offline and, for lack of a better word, save the circuit. Your wire's not going to burn up. Your equipment's not going to burn up. Wire itself feeding the load is basically a giant fuse. That's all a wire is. So if a wire is rated for 100 amps, you're looking at the size of the copper, the diameter of the copper that's in that wire and the insulation around it. And the more amps you run through there, from 100 amps up to 200 or up to 400 or up to 600 amps through this 100 amp wire, if you open a fuse up, it's going to be almost the same thing. It's copper that, as it gets hotter, it's going to lead towards failure. Short circuits are also a failure mode, but rather than an overload, which is a lower current over a longer time, a short circuit is a higher current over a shorter time. So when I talk about a short circuit, I'm changing the normal current flow through the wire into the load into a path of lower resistance. For example, if I go with a fork and I plug it into the two holes here, I'm creating a direct path with little resistance between two of the phases, or the phase and neutral. And with that less resistance, the current will shoot up very rapidly. And that's where you want to take things offline very quickly. And just by thinking about the overload and the short circuit, which one has the tendency to be more dangerous for the facility or the people working on the equipment? Overload or short circuit? Short circuit. Short circuit can be a very dangerous situation. And when we talk about danger in electrical distribution, we're talking, you'll hear the words arc flash energy. And I don't know if you've talked about that yet, but arc flash energy came into the code, and the awareness of it, I guess, became more prevalent in the last 5 years. Arc flash energy is if I have some type of short circuit, and in reality, you'll look at a flash, a bang, a puff of smoke, anywhere from just a little flash, bang, puff of smoke to, did anybody watch that, what was it, the San Francisco Monday Night Football game? 49ers were playing, and all of a sudden all the lights went out, and they had that camera, and you saw this big blue bang out, that was a block away. That would be a short circuit. And it looked, you were a couple of miles away in that blimp, but if you'd have been standing there, you'd have been blinded or hurt, or you'd at least got the bejesus scared out of you, because those are pretty dangerous situations. Now, how dangerous, there's really two factors that come into play on how dangerous this is. How much arc energy is available, the amount of current available flowing into a fault, and the time that current is flowing into a fault. So the amount of current and the time equal the arc flash energy, and what that energy translates is how bad the explosion is going to be. What that translates into the real world as a contractor, for example, who's working on the equipment, is how much protective gear do I need to put on to work on the equipment. If I'm looking at just a circuit here, I'm way downstream, I've got a single phase type application, it's probably not very dangerous. I could probably go into a panelboard in here wearing some gloves, protective coveralls maybe, and some glasses. And if I go out to that transformer that exploded on Monday night, and say I had to go in and work on that transformer hot or something while it was still active, I would have to wear, basically it'd be looking like you'd be wearing like a nuclear suit to go in there to try and protect yourself. And these are dictated by the NEC code. They look at arc flash energy, and once you calculate that, you determine how much protection you need to work on that equipment. So we've got just a couple pictures here on the different types of faults or short circuits available. You've got a line to neutral fault, which is, say, on a 120 volt receptacle. I'm creating a path of low resistance, but still resistance between A phase and neutral. Line to line, between A phase and a B phase is a fault. Line to neutral can be a fault. And then the most dangerous out there is the three-phase bolted fault. All three phases are tied together. When you talk about the most dangerous situation, what is going to be the most dangerous situation? It's going to be three-phase fault. They call it the bolted fault, and that is the worst-case scenario when we talk about how UL dictates in NEC that we need to build our equipment and that the people need to be protected that we're working on the equipment. Everything relates to the worst-case scenario, which is the three-phase fault. How often does that happen in real life? Not that often, believe it or not. When it happens, it's usually in when you're starting the equipment up for the first time. You go in, contract, you install equipment, you're putting everything together, and maybe somebody accidentally leaves his wrench sitting across the circuit breaker, and it's close enough to the phases where electricity can travel through air. Remember that. Air is resistance, but it can still travel through air. And, that could be a situation when you first turn on the equipment that you basically get all three phases tied together in a worst-case scenario. Once you're up and running and your power system is being used, this is less likely, and you're more likely to get one of the other types of faults. So I touched on this. The electrical distribution system will produce a maximum fault current that depends on the available fault current from the power company and the impedance in the system at the point of the fault. So every building is going to have a different maximum fault current. And when you construct a building, the utility will come in and they'll give you the power. And utility will be responsible for telling you the maximum fault current at this point is 65,000 amps, or whatever that is. And what are some of the factors that come into play for them? How far are you from a transformer? How far are you from a generating station? How many other customers may be on this same grid that you're on? Excuse me, I'm on the verge here of a head cold thing, so bear with me. So the impedance, the other part is the impedance of the system. And what is the distribution system? What is the largest thing that you think about when you're talking about impedance? Talking about cables. So once you come into that building, electricity's got to flow through all the different cables, all the different points in your facility. And for each foot of cable that you're moving, being cable is impedance, you're lowering the fault current as the farther you go into your distribution system. So at this point, I'm a long ways away from that transformer that's sitting at the end of the block. So if it's 65,000 amps available there, by the time a fault occurs here, there's so much impedance through the system that maybe I'm only 3,000 amps fault current here. And that's one of the key design elements. If you're starting and designing, whether it's a consultant or a design build contractor, that is one of the most important elements to take into the design. Also, that factors into cost. Just thinking about it, the higher the fault current, the more rugged we have to make the distribution equipment. The more rugged we make the distribution equipment, the more it's going to cost and the more we're going to charge you. And that funnels all the way back to the owner. NEC requires that all protective devices be rated for the short circuit current available at the supply terminals. So your first switchboard as your service entrance, maybe 65,000 amps, it will have to be labeled and rated for 65,000 amps. By the time you get into this point in here, I'm actually will be much lower. an engineer or the engineer of record will have to do a short circuit study, basically they call them. And the short circuit study will then factor in the calculations of the impedances of all the cables, and you can look at an entire distribution system like this and be able to look at all those different points and tell you what the fault current is at all those different points of the distribution system. That's required by NEC. UL then takes what NEC requires and translates it that short circuit rating of the assembled panelboards or switchboards must not exceed the rating of the lowest device in the assembly. And I'm going to put an asterisk on there that we'll circle back to. So if I've got an assembly of a panel board and I've got 10,000 amps available fault current, the least rated device in that panel board has to carry that 10,000 amp rating. So looking at how it would normally look, coming out of that transformer, I may have 65,000 amps available here, 25,000 amps fault current available at a distribution panel, 50,000 amps involved in this distribution panel, and only 4,800 amps in this lighting panel. Pretty big spread. If I'm looking at this just at one glance, I see this is 65 and this is 50. This distribution panel is probably going to be near this switchboard. This distribution panel at 25 amps, there's two things that are going to mean, they're going to lead to it being a lower fault current. Number one, it could be twice as far away, so you could have twice as much cable feeding. Number two, it could be a much smaller ampacity rated. So this distribution panel, maybe that panel is 1,200 amps. Maybe this distribution panel is only 200 amps. And why would that be a difference? Because 1,200 amps, you get bigger cable. 200 amps, you get smaller cable. And when you think about a bigger cable, what's on the inside? It's all copper. The more surface area, when you talk about the cross-sectional area of the copper cable, the more surface area you get, the more those electrons can fly through with no resistance. Most of the resistance will occur around the edges where you're actually bumping up against the insulation, and this is imaginary, but this is how it actually works. The electrons don't move as quick along the edges. So the more copper you get in the middle, or the bigger cable, the more you will have a higher fault current. Here's another one. This one dropped noticeably down to 4,800 amps. What's different about this lighting panel? Well, this is 48277. It's a dry type transformer that's stepping it down to 12208 for your lighting panel. And this could be the exact same distance as this one from the switchboard. So what's different? What's the key? Why did a fault current all of a sudden drop? It's dry type transformer. Anytime you put a dry type transformer in your distribution system, you basically will set a new maximum available fault current on the secondary side of it. And it's the transformer itself has mechanical limitations on how much energy is going to couple from the primary to the secondary of that transformer. When I say couple, think about a transformer. You've got the primary voltage. It's magnetic, so you're wrapping it around an iron core, and you got secondary, which is magnetics, picking up the other side of the field. And that process has inherent impedance built in because you're not direct connected. There's no direct connection. It's all magnetics between that transformer. So on average, you're looking at about a 5% impedance fixed in right there, and that's probably going to be one of the highest impedances you're going to find in your distribution system. If you think about, and what do impedances or losses in the transformers, what does that equate to? That's money. You pay for $100 worth of electricity, and 5% of that is impedance. You take 5% of your $100 and you might as well just throw it away. So if you look at a large facility like a data center. Data centers are the most energy conscious facilities that you can build. And if you're not familiar with a data center, it's a building where that probably doesn't even have any windows and it houses all the computers. So if you think about like a Google, who they've got an acre in acres of computers or servers that handle all this. And all those servers generate heat. And the only thing the data centers do is take energy in to run the computers. I won't say the only thing, but that is the majority of the load on that data center. So how much does it cost to run a data center is how much energy they use, so that's a large chunk of it. So when they look at designing a distribution system for a data center, they look very hard at, let's remove as many of these dry type transformers as we can. And you've been seeing a lot of changes on the voltages of data centers where instead of stepping down to 120 or 240, they're doing things now at around 400 volts. A higher voltage means you've got you may be able to get by with just one transformer that steps it down and be able to use that across your facility. Yep. Yes, you could. But that's the problem. What Excel will do is, in the old days and I'll say 5-10 years ago, before energy efficiency really became a hot button, Excel Energy, downtowns are a great example, but even in the suburbs, it was very common for them to come out. They'll take their 15,000 volts was a good distribution voltage for them. So they'll come in with 15,000 volts. Excel would put the transformer in and hand the customer 480 volts, exactly like what you're saying. So they would meter on the 480 volt side, and then the customer would basically have the voltage he's going to use. Excel got smart, I think, and they realized, why do we pay for all the losses that all these transformers are putting out there? And historically, they've done that. So they are doing more and more of handing the customer 15 kV or a higher voltage, so the customer has to come in, take the 15 kV, put in their own transformer to step it down to 480 and use it, and then the customer ends up eating that money. So, I mean, that's a very real industry question right now. You know, like, utilities kind of have a monopoly, but they have to work with their customers on a regular basis. You know, I think one of the things Excel's been doing is they're not forcing it necessarily. They're offering incentives to get the customer to take the 15,000 volts. So the customer always has an option, but Excel will say, if you take the 15,000 volts instead of the 480, I will give you a lower rate or a better incentive or what have you, just so you take that loss responsibility on and not me.
So there's not like a code standards, like incentives from the company itself then?
Yeah, each utility, and you know, I don't know how many there are, but there's got to be hundreds, you know, around the country. Here we're Excel Energy, which used to be Northern States Power, that did Minnesota. Now Excel Energy keeps growing, and you got everything from Colorado to here is Excel Energy. But even amongst Excel Energy's territory, you've got electric utility co-ops. Co-ops crop around anywhere, and they'll buy power from an Excel or a Great River Energy or some of these other power creators, and then sell it to their I don't know if neighborhood's the right word, but their little group that they're responsible for. And so co-op may not necessarily even have the same guidelines that Excel is having. So, you know, there's no standard, no. It's still driven by what the utility wants to do. You know, and again, there should be a standard. But it's probably part of the process of going from a monopoly and a utility being a monopoly. It's not like you can shop which utility you want to use. Now, I think they started to do that, and was out there, maybe Enron with a big name that kind of led into how do you shop utility. That didn't work out too well. But, that still may evolve into that, and we're kind of in that process right now, I think, and well, how does it make most sense for everybody involved?
You can buy Westinghouse in its entirety or a division that produces this type of gear?
Yeah, Westinghouse made had a couple of different divisions. The divisions that Eaton purchased was called distribution and control. So that was all their electrical stuff. What we didn't buy was the Westinghouse light bulbs, which turned out to be a good idea because you can't make them. The Westinghouse. The big loser, I think, in 1994 was Westinghouse, I believe, bought CBS, if I'm not mistaken. And they got into the entertainment industry, and it just was the big loser. So Westinghouse itself was financially unviable because of non-electrical stuff, and it kind of caused them to have to shut things off.
So like the nukes and the jet engines and stuff are still playing.
Yeah. The Westinghouse Nuclear Group, I believe, they're still around. Now, they've probably had nothing to do for the last 15 years, but maintenance and stuff. But now, nuclear energy is, there are plants in the design stage, a couple that have been already permitted, that are going to be built. So, last nuclear plant, I believe, was 75-ish, give or take, in the United States. And there's already a process now of more nuclear plants coming online. So, it is coming back. All right, that was kind of just a quick overview. Now I've got going to go on to some specifics on panel boards and then some specifics on switchboards and Eaton's products on that, as well as some general terms here. So on panel boards, we'll just talk about what is a panel board, the different components that go into the application considerations. So the definition of a panel board is a wall-mounted electrical power distribution device for use in commercial and industrial applications. Wall-mounted is the key on this one. Provides the circuit control, which is I can turn a breaker on and off to isolate my circuit, and overcurrent protection, which is for faults and overloads, for light, heat, power circuits, anything that you plug into. A panel board itself comes in 3 parts. We've got a box, which is just sheet steel. So this is sheet steel that you hang on the wall. You've got a chassis, which is the bus. You've got a main breaker or main lugs on it. The feeder breakers in there, your vertical bus, and this whole chassis is built all as one assembly. So when this comes to the field, take the chassis, mount it into the box, and then on the outside is what they call a trim. The trim basically goes in front of the chassis to make it it looks pleasant and it's safe. That's basically for the protective covers, so anybody just can't come in and touch things and turn breakers on and stuff. So looking at the chassis, there's basically 3 types. There's main lugs only, main circuit breaker, and main fusible switch. And if you have main lugs only, what protects the chassis itself? If I've got 100 amp busing in this chassis, I got all these 20 amp feeder breakers, but if I got a fault on this chassis itself, you don't have a main breaker to protect it. You go upstream to the switchboard breaker that feeds this, that actually is protecting that bus. Now, looking at this, which do you figure is the most cost-effective design? Main lug only or main breaker? Main lug is more cost-effective just because all you're doing is taking out this main breaker. Well, that has costs. Now, if you're an electrician Which do you figure you'd rather have? The guy who's actually working on it. You want the main breaker, so when you walk up to the panel board, I can turn the breaker off, work on my circuitry. When I'm done, turn the breaker on and move on. If I don't have that breaker there and I'm working on a main line only panel, I have to go to the switchboard. Maybe that's 100 yards away or 50 yards away that I have to go. Open that breaker, lock out, tag out, follow all the procedures, come down here, add my 120 amp circuit that I'm adding, and go back up there to, re-energize this panel. So there are benefits for having this main breaker local disconnect. It costs a little bit of money, but has a lot of value to the actual guys who are working on the equipment.
Do they come with a switch that doesn't have overcurrent protection?
They do. They do. This inherently will come with two types of overcurrent protection built in. They call it a standard circuit breaker, like this one. This is exactly that circuit breaker there. It's going to have, they'll call it a thermomagnetic circuit breaker, and you're talking about the trip unit type. So this one's a little small. This one here is a 400 amp breaker. Okay, and right here is the trip unit itself. Okay, in these smaller ones, you don't have access to the trip unit. They're more cost effective. This one, with the larger you have, the more you have access. So the trip unit itself, you'll have the two styles of trip unit. You'll have a thermomagnetic trip unit or a solid state trip unit. Solid state trip unit is just like it sounds. It's looking at the current that's going through this breaker, and the CTs, current transformers, are embedded in the circuit breaker, and at real time it can look at the wave of the current and how much is flowing through, and you can get really precise on dialing your protective settings in your circuit breaker. The most cost-effective means, and what is usually used on the smaller breakers, is the thermomagnetic trip unit. The thermomagnetic trip unit has two protective features built in, the thermal and the magnetic. These are manual protective features. There's no solid state circuitry in there. There is a thermal protection, and remember when I talked about the two types of faults, you have an overload. The overload fault is protected by the thermal feature, which if you took the skin off this, there's actually a couple pieces of metal in there, different types of metal, and as the current flows through the circuit breaker, the metal heats up at different rates. So you have to do some mechanical design on these metals, and once you break the 100 amp, if you have a 100 amp circuit breaker, once you get over 100 amp, one metal will start to bend more than the other, and that will then eventually lead to the circuit opening up. And that's how overloads. So you can see how overloads can take time to actually trip offline and open your circuit breaker. When you talk about a short circuit current, you're talking about the magnetic portion of a circuit breaker. So the magnetic portion of a circuit breaker, different manufacturers do this differently, but basically you can have your two contacts together, and as your current ramps up very sharply on a short current, remember you get a high current fault in a quick time, the magnetics associated with that high current basically can blow apart the two pieces of metal, or the contacts, basically. So they'll force to be open at a much quicker rate. And those are actually two physically different pieces right next to each other in series inside the circuit breaker that offer those two different methods of protection. Did I get your question?
Yeah, and so if you order it with the full protection, or just an off switch?
Yeah, okay, yeah, that's where I was going with that. So that would be the standard, and that's just called a molded case circuit breaker. Now, there are means where you just want this disconnectability on there. You don't want that extra protection because it messes up your coordination or whatever. And there's something called a molded case switch. The molded case switch is a thermomagnetic circuit breaker without the thermal or magnetic. What it does have inside is what they call a fixed instantaneous override. And that is in all breakers. That is in the thermomagnetic one as well as the molded case switch. The fixed instantaneous override is, I'll call it a self-protective feature. It varies on every individual breaker, but basically you're talking about, say, 14 to 18 times the rating, the trip rating of the breaker. If you get a fault current that high, basically the magnetic part will kick in and open up. And they do that because if you have a high fault current, the number one thing at that point is safety, get something open. So if I don't open the circuit breaker, you got a good chance that the contacts inside here may actually weld together. And if those weld together, it could happen to all the other circuit breakers in there. And then you've got a fault current and nothing's opening, and then it can get real dangerous. In motor control centers, as we're talking about these, they have something called an HMCP, which is similar to a molded case switch. It's got the magnetic protection in there, but not thermal protection. And they use that in conjunction with overload relays that are specifically set for the motor. So those are kind of the three different methods of circuit breakers. Oh, and the last one on here was the main fusible switch. When I talk main circuit breaker or main fusible switch, they're kind of the, it's really the same concept, except you're using fuses instead of circuit breakers. Which is by far the better way to, what's the better method to use, circuit breakers or fuses? Circuit breakers. Why? Well, we don't make fuses, so. But fuses are the way they used to do it in the old school. A lot of people still use fuses today, and you'll never get them to change. But circuit breakers have a much greater advantage, or a longer list of advantages than what a fuse could offer. In things like circuit breakers are much smaller. You can get much more selectability on your trip settings versus a fuse, which is fuse going to be what a fuse is going to be. When you're talking about a low-level short circuit, fuses can work very quick at a high-level short circuit, what they call a current limiting mode. Once you get into a high enough high enough fault current, that fuse will blow off pretty quick. But when you're talking a low energy short circuit, fuses can be, I'll call them inherently dangerous, because it can sit there for a long time letting the power flow through, waiting for that copper inside the fuse to melt. Now a circuit breaker on those low levels are going to work much quicker and take the circuit offline. So in those instances, your circuit breaker is going to be much more safety conscious than fuse. Circuit breakers also, you can do a lot of things with circuit breakers that are tougher to do with fuses, like adding ground fault protection. Pretty easy in a circuit breaker. You can't necessarily do it with all fuses. You have to get a really big fuse to do it. Accessories, if you hear things on a circuit breaker like a shunt trip or an auxiliary switch, these are devices that you can actually mount inside of a circuit breaker. And you can open and close a circuit breaker remotely. So on a panel board, you've got two options. Okay, and the things I'll bounce through when you're designing a panel board, these are the things that you need to take into consideration, not only when you're designing it or specifying it, but if you're a contractor and you're ordering a panel board, these are the things you'll need to know, because we'll build it this way. So panel boards can go either top or bottom feed. And we'll put the circuit breaker, the main circuit breaker, accordingly on the right side. The trims itself can be surface or flush. What do these actually mean? Well, the surface trim is, I'll take my panel board cam, the sheet steel, I'll basically bolt it to the outside of the wall so it's sticking out 6 inches, and put my interior in, and then I'll take the surface trim on the front of the panelboard box. A flush trim is where I take my panelboard box and I mount it inside the wall. So like new construction, for example, a lot of people mount panelboards inside the wall. Like this one, it's embedded inside the concrete. Hallway in a school, for example. If you have to have a panelboard in a hallway to school, you'll embed it in the wall. Or a prison, you keep things much more isolated that way. Now what the flush trim will do is it takes the same surface trim and it basically adds
Todd, you might have to put the marker down and just put it down back. Yeah. Pick it up now. Yeah. That's trick.
holy smokes. So it adds this extra 2 inches or so overlap around the outside of the surface trim. Why is that there? Well, it's aesthetics, I guess. It covers up the gap between the drywall and the panelboard can itself.
It's
Okay. A couple of modifications you can do to a panelboard trim are what they call fast concealed trim clamps. I talked about the hallway example where you don't want people to have access. You can see there's a couple of bolts here on the side of a normal trim that you remove in fast concealed trim clamps. So it takes some of the hardware from the outside and puts it on the inside. The other one is a door and door trim. Door and door trim basically is pretty much just what it sounds like. You've got your normal door. That again. Oh.
go back. It's not enough. Go back where you want and put the marker. I'm sorry to do this. Few tricks now. You can go. There you go.
Okay. All right. So the
Oh, you go to the second one. You have to do it again. Sorry, God.
that's all right. I'll learn this thing. Okay. So the door and door trim. You've got your door on the inside, okay? And that's the door that you open, just like this door here on the wall here, where all your circuit breakers are behind there. These are all your feeder breakers stuff that you're going to turn on and off. You'll see no wiring or anything in the side. That's when you open this door here. That's basically what they call a dead front. So when you open it, you'll see circuit breaker handles, but you can't grab any wires, and it's not an unsafe position to be in. What the door and door feature adds is you can see there's a hinge right here, and bolts here, here, and here. And if you take off all these bolts, you can basically take this whole thing and swing it open. And what that's going to give you is not only your breakers in the middle, but all your wiring in the gutters. So when you think about a contractor doing an installation, and OSHA is very particular about leaving covers off while you're doing work. So they'll have their circuit breakers, they'll connect their circuit, and then they'll probably go out to the load and check their circuit, and then they'll come back, add another circuit. Well, then it's time for break. Then you got to come back, add another circuit. And every time, then you got to go back and check it, and then you got to do lunch. And all these times that they're coming and going from the panelboard, OSHA mandates that you have to have that panelboard covered. So when you leave, the next guy doesn't walk up and say, hey, why is this panelboard open? Reach in and grab something, and it's live and a dangerous situation. So panelboard trims are very user-friendly, and I'm positive they're preferred by pretty much every contractor around.
fast concealed is the one that's preferred?
The door and door.
The door
Yeah,
and door.
fast concealed is a more of a aesthetic or access issue. Just taking as much hardware away from the front as you can. Door and door is the one that actually helps on the installation.
And probably it's tamper resistant, so people can't tamper with the panels.
Yeah,
It's for
exactly.
people to put them in schools and jails, so people don't go kill themselves intentionally or accidentally.
Yep.
So he can just take the outer hinge, open that up and close that.
Correct. Correct. So in the fast concealed, for example, don't we all know a guy in high school who had a dime or something who would go to those panels and unscrew things just for the sake of unscrewing things? So that's what you're kind of preventing with the fast concealed trim clamps. Now, these features here have been around for a number of years, and they're pretty much recognized in the industry of different options you can get for panelboard trims. Now, what Eaton did is we kind of took this concept one step further and changed our standard panelboard trim to what we call the easy trim. The easy trim has the concealed hardware and the door and door as standard. So if you, and we did this too until we changed this trim a few years back. If you want the door and door feature, you may have to pay $50 a panelboard. And if you got 100 panelboards on the job, do the math. Same with fast concealed trim clamps. It might be $50 a panelboard. All of a sudden you got $100 a panelboard adder on a panelboard that only costs $300. It can get kind of cost effective because us and our competitors, the Square D's, GEs, we're not steel manufacturers. That's not the core of our business. We're circuit breaker guys and power distribution guys. And so when we have to do the special things with the trims and the dead fronts and things like that, it costs more money for us to do. So that's why we kind of changed this, the whole concept now is the easy trim, and this is standard. So you get those two features built in. When the other thing we did is we talked the installation time about the trim. I had said you got to take it on and take it off, and if you don't have the door and door, and whether the engineer didn't specify it or the cost is driving the project, you just don't have a door and door, and if you're a contractor, it can be very difficult trying to cover that every time you're trying to hook a circuit up or take a break or take a lunch. So the easy trim has the ability to be mounted in less than 20 seconds versus 5 minutes for a standard trim. Not even the door and door, just a standard trim that you have to put your bolts on. And think about from a contractor standpoint, the dollar size, the dollars that are associated with taking trims on and off, and you're trying to estimate a job, and you're trying to figure out how many times does my field electrician have to put a trim on and take a trim off, put a trim on and take a trim off. And if you can factor in how much time you can save doing that, I guess that's one of our, when I talked about us being an engineering company, this is one of the developments that we came out that it kind of added a whole new feature to the industry that it just didn't exist before. And you can do this with no tools on it. Here's kind of just a snapshot of it. The key is the hinge for the notch in the bottom of this trim. So you can see the trim is just a solid piece. It's got no screw holes. It's got no nothing else on the front that's going to get in the way. And basically you can take this trim, you set the notch onto a panelboard box, has a strip on it, set the notch into the strip, and then the door can kind of close itself, and all the pieces here kind of just fall into their associated notches, and then the door kind of swings shut, and basically you just give it a quick lift and it drops right into place, and then it's got the normal lock here on the front of the panelboard that all the other panelboards have to lock it out safely. Pardon? Free. Literally. This is our standard, so we charge nothing for this. We just do it because we like contractors to drive their business to us. So yes, we gather money for it indirectly by increasing our sales. So if we sold $1 million to this contractor last year, and he likes our panelboard trims because it saves him money, and it's all driven about the money. If he saves $10,000 a job, well, then he'll say, hey, that next order, let's go with Eaton Corporation because they will save me $10,000 a job. And that's why we do it. Many times you will get into the need for multiple panelboard cups. When a panelboard must be furnished in more than one section or more than one box, each box must be furnished with the main bus and terminals of the same rating unless a main breaker is in each section. So panelboards come in what they call certain chassis configurations, whether it's 18 circuits, 30 circuits, or 42 circuits. And that tells you how many poles you can put in there for feeder breakers. Up until 2008, 42 circuits was the largest that NEC would allow you to put in a panelboard. Any state that has adapted the 2008 or newer NEC code, that 42 circuit restriction is gone. So today, the only limitation in how many circuits I can put in a panelboard is physical space. Literally, can it all fit in there, or do I need another panelboard? So if I do get in a case, whether I'm not for code or whether I just like to keep my panelboard small, because if you think about it, if I put 84 circuits in one panelboard, you're going to have bundles of wires coming out the sides, and it just may get too cumbersome for someone's preference. So if I got 84 circuits and I want to do it side by side, panelboard next to panelboard, the two options are sub-feed lugs or through-feed lugs. And this is one of the, as straightforward as this concept will be, it's one of the least understood ones that you get a lot of questions. Well, what's the difference? Well, the difference is, I guess, the power flow. So for sub-feed lugs, your first panel on your incoming cables has main lugs, not a circuit breaker. And then the main lugs, you can daisy chain. This is basically a double set of main lugs, so you can daisy chain to the next one. So the power of both panels flows through their individual chassis and connects at this point right here on the lug to go upstream. It's common when you do this, do this side-by-side panel, to make both panels the same height. So this is going to have double lugs, this is going to have single lugs, and maybe you've got 42 circuits here and you only need 18 more circuits. Well, you could probably build this in 60 inches high and this one in 42 inches high. But aesthetically, it really ain't going to look that good. And if you're making this connection straight across the bottom, it's much easier to have those panelboards the same height. So a lot of times you'll make the second one taller just so it looks like a big square or rectangle versus kind of offset equipment. Physically, this is what it's going to look like. You may have a 100 amp panel rated for 1 cable per phase incoming, and you'll put 2 lugs on there. And this is a mechanical lug. If you see, that's another thing to point out, I guess. Mechanical lugs are these screw types that you're seeing here. So you can take the lug, put it basically put it in a hole for the lug, and then screw down the terminal, and that tightens on the copper to make the connection. The other method is the compression lug, where you actually take a metal device over the end of the copper, and that metal device will have the termination on the other side, and you crimp that down tightly to make your connection. Physically, in a panelboard, a mechanical lug is much smaller. So if you have to go to compression lug, whether it's an owner's requirement or what have you, you're usually going to get taller. And if you're talking on a feeder breaker, You breakers themselves, for all these breakers here I have, the only lugs you can get are mechanical lugs.
What's the advantage of the advantage of the compression? Or?
Well, I believe a compression lug will maintain its compression over a longer time. Yeah, if you think about the cable, a building, a school is a good example that you run a lot of load during the day, and then at night everything drops down. Cables, being they're made of metal, copper usually, sometimes aluminum, but mostly copper, have what they call coefficients of expansion. So that copper is going to expand with a lot of current, contract under normal conditions, expand when more current comes through. So every time that expands and contracts, if you think about the mechanical lug, it's going to be inside of that lug, and gradually over time it'll loosen. And so with mechanical lugs, you do probably have more of a susceptibility to loosen over time. And I always say a proper maintenance schedule, as followed and enacted in a facility, will catch that. You see a lot of, now one of the things on maintenance schedules, a lot of people today do heat scanning or infrared scanning, where they can take a picture. They can go into each panel board, and they'll do this once a year or twice a year, or whatever their program sets up. And you can take a heat scan picture of the front of the circuit breaker, and you can look at the circuit breaker, and it might show normal temperature, and bright yellow on this one terminal. So you can decipher A, B, or C, and if you get that bright yellow picture, that's going to tell you this is a hot spot. And why is it hot? Probably the terminal's loose. Could be something else, but that's the first thing to check. Now, with that said, you still need to do your same maintenance procedures on your compression lug, but your chances, I think, are that it won't loosen as quickly. Okay, so those were the sub-feed lugs. The through-feed lugs. Notice here we've got our incoming cables. We're actually putting the lugs for the second panel on the other side and making that connection over there. And why this would be an advantage, if you wanted a main breaker, you can put a main breaker here instead of main lugs, and then put your main breaker on this side, lugs on the second side, which jump right over to this one. Again, you want to keep these the same height. Now, how come I can do a main breaker here, but I can't do a main breaker here? Because of double lugs. Okay, and when you think about a circuit breaker, when I build a 225 amp circuit breaker, the biggest thing driving the size of this breaker is how much space do I need to land my lugs. I suppose if we had wireless conductors, for example, I could probably make this circuit breaker, like this or smaller. So I'm forced to make it big to get the lug size. Now that's probably, I probably stretched it a little bit, but conceptually that's something to think about. So when I make this 225 amp breaker, I design it from scratch, and you're talking a lot of dollars invested in R&D. So these circuit breakers, they're designed to handle lugs for 225 amps. Now, if all of a sudden, which is one lug per phase, but if all of a sudden I had to do 2 lugs per phase at that same rating, I'm going to have to figure out a way to make this circuit breaker bigger, or use, something like this to handle this. So generally speaking, that's why we can't do sub-feed lugs on a main breaker. Okay, this is what this will look like, and it's almost a flip it right side up, upside down, lugs on both sides. So the panelboard sizes are restricted only to the physical limitations with the NEC coming in of the standard box heights and widths. How much stuff can I put in the box? I mentioned NEC 2008 doesn't limit you to circuits anymore, so that's out the picture. But NEC does have a requirement that the top operating handle, and if it's top feed, it'd be the main breaker, that handle has to be mounted no more than 6'7" off the finished floor. What's so magical about 6'7"? Right? Something to do with this. How high can I walk up and turn that off in the case of some fault happen? I need to turn this thing off. Now, if you're a 5'1" electrician, this probably ain't going to help you because you're going to be in trouble either way, but it covers the majority of cases. Additional box in front's required when the components exceed what can fit in one. So here's the codes we talked about. UL. UL is a manufacturer's industry, I'll call it, direction on how we have to manufacture our products. NEC has nothing to do with how we manufacture products. It has to do with how these products are installed and operated. So UL and NEC, although they're both used interchangeably and kind of apply to the same thing, UL is directed towards the manufacturers. NEC is directed towards the installation. So naturally, we have to manufacture things that meet the installation requirements, and the installation has to meet the UL requirements, but that's basically the division there. NEMA is just the manufacturers association standards, and we get together. We are part of NEMA as well as the other manufacturers, and we'll put together things like standard operating procedures, standard maintenance procedures that you might see a lot of commonality between us and our competitors on. Here's the things you need to do to maintain the equipment over its lifespan. And of course, there are federal specifications that are different than what we've done here for certain federal projects. So now getting into the actual Eaton panelboards.
Can we have 5 minutes break?
Yep, that's work.
To the users?
Yep.
Okay. Give me a break here. Some water?
Oh, I'm good there.
Okay.
Good there.
Give me a few seconds here.
Okay. All right, so we'll jump back into it. I just kind of now head into from the general panelboard discussion into the Eaton specific family. And you could have me and my 3 competitors all stand up and tell you exactly what our families are. And try and remember that, but you probably won't. So soak as much of this in as you can. But I think all our manufacturers kind of have the same concept in that we have a range of panelboards from the small to the large. And our family is called the Powerline family. We've got Powerline 1A, 2A, 3A, and we'll call those lighting or receptacle panels, and 4B, 5P, 4F, which I'll call a power distribution panel. I think I got it.
Yeah, I know. I just. Oh, wow, you're good.
Yeah. Some
sorry.
assistance.
Oh, you guys are give him the trick here. Where was I here? View full screen. I'm sorry.
Yep, that's right. You know, so there's a wide range, and everybody's got a family name, and ours is the Powerline. Okay, so when you're looking at a panel board, there are selection and pricing factors listed up here that all come into play in how much it's going to cost and how you actually design it. And I think we've talked about these by now, but when you go to your manufacturer, whether you're a contractor or if you're an engineer and you're trying to put down something on paper for somebody to actually bid off of, all this is the information that's required to take that next step. So your service, voltage, and frequency are the main one. Service meaning delta Y, voltage, 480, 277, or 208, and frequency. And of course, if you're in North America, we're 60 hertz. But if you go overseas, you might be 50 hertz. If you go down to the ground, the airport runway, you're going to be at 400 hertz. So there's a couple of oddballs, but basically 60 hertz covers us in North America here. Your ampere rating, the type of main, whether it's main lugs, circuit breaker, or main fuses. The short circuit current rating, okay, the maximum available fault current at that device itself. And then you look at your branch circuits, the number of branch circuits, type, and the ampacity of each individual branch circuit. The other thing is environment. By default, everything that we provide is going to be what they call NEMA 1. It's going to be indoor rated, and that's about it. If there are different environmental factors that come into play, those also need to come into play likely in the panel board. So for an outdoor application, they have what they call a NEMA 3R, which protects against rain coming down. But if you read how the protection works, it doesn't protect against rain coming sideways or a hose going sideways. Then you move into other classifications. There's a classification for an environment called a NEMA 12. NEMA 12 is dust type. So if I built a facility and I happen to be running a sand plant and I've just got a little shed out next to the sand plant that is a panel board, you maybe want to consider a dust type one so sand doesn't get into the panel board. What does environment mean inside a panel board? It means countdown to failure. Whether that environment is rain or dust, or in the next case, certain gases can come into play. When I say that, I'll take example of a water treatment plant. A water treatment plant has a lot of different gases in the air that they use to process with the chemicals. I think the biggest one you're going to hear, it's, don't quote me on this one, but something like hexyl, sulfur, fluorochloride, yada yada. And this is a chemical that eats away from copper, for example. So in that case, you have to be careful where you're even putting the panel board, because no matter what enclosure you have, the air itself may get to the copper. But for other environments, an outdoor environment, for example, we have what they call a NEMA 4 or a NEMA 4X panel board enclosure, and these are either stainless steel or plastic enclosures that the panel board goes in rather than just a normal steel. The last one on the list is fully rated versus series rated, which we haven't talked about yet, and that's the asterisk question. So short circuit current rating, again, the short circuit withstand, that's how much the chassis can withstand. So if I've got 65,000 amps available fault current, you have to build the panel board chassis rated to 65 so everything stays together in one piece under a fault current condition. In addition to that, the interrupting rating of the overcurrent devices has to carry that short circuit current rating. When I say interrupting rating, I'm talking about, there's two ways. And the first one is the short circuit withstand rating, and the second one, it's the circuit breaker interrupting rating. And these terms are, I'll say, sometimes interchanged or often not misunderstood. But when we talk about withstand rating, it's the ability of a panelboard chassis or even a circuit breaker to sit there and handle the fault current without exploding into pieces. It may be waiting, in the case of a chassis, it sits and waits while an upstream device may be counting down to a trip. When we talk interrupting rating, it's the ability of the circuit breaker itself to open and interrupt the flow of current at 65,000 amps. So, you know, I can tell you this breaker here is rated for 65,000 amp short circuit rating. And that means it can interrupt 65,000 amps. So if 65,000 amps is flowing through this small circuit breaker, that the contacts on this side of this breaker are going to be able to open up and break that current. And generally, when we talked about fully rated and series rating, then fully rated means all the circuit breakers in that panelboard have to be able to interrupt that 65,000 amps. So now looking at the other one that we didn't necessarily touch on yet is series rated. So your fully rated is where all the devices have to be rated for the short circuit rating at that panelboard location. A series rating is when a short circuit interrupting rating assigned to a combination of devices, 2 or more, basically 2 or 3, in series, and which a rating of the downstream device in the combination is less than the series rating. So what that means is these devices here may not all be rated 65,000 amps. I may have to use this type of breaker for my main and this type of breaker for my feeder breaker. And say if this is 65,000 amps and this is 10,000 amps, and I looked at which one is going to be the most cost effective, okay, just by looking at it, you're going to say this one's got to be cheaper. But it doesn't meet the rating. So NEC came out with something called, that UL came out with something called a series rating protection scheme. So what that means is you've got a fully rated panelboard, 65,000 amp main breaker, and all your feeder breakers are rated 65,000 amps. If a fault occurs on the load side, your current can flow through any of these breakers, and any of these breakers can trip and take the fault offline. In a series rated panelboard, I still have my 65,000 amp rated main breaker, but I'm using 10,000 amp rated feeder breakers as branch breakers. And what our UL testing tells us is that if a fault occurs in the same location, it still has the ability to take this fault offline, no matter whether it's the 10,000 amp breaker or the 65,000 amp main that are tripping. And the only way we can get by with that, what I would call providing an underrated device, is because we took these breakers and went to UL, put them on a bench test, and blew 65,000 amps through them, and proved that the breakers will do the job. And conceptually, how can this thing see 65,000 amps? That just doesn't make sense if it's only tested for 10,000 amps. Circuit breakers themselves, as the fault starts to propagate, when you start to ramp up from 100 amps up to 65,000 amps, as you're ramping up and the fault's getting worse, circuit breakers inherently are current limiting, is that the contacts of the circuit breaker are going to start to open, and they're going to begin the tripping process while your fault current is starting to go. And as those contacts are starting to open, you get a little arc between those contacts of 65,000 amps. And those arc between those contacts is traveling through air. So what you're doing is actually adding a little impedance inside there, therefore lowering the value. And being you've got a head start on opening You're not starting from ground zero at full 65,000 amps just because of alternating current. You know, you start at zero and you work up and then you go down. Just because of that, your contacts are going to have a head start and start opening. So that's why one of these two breakers, I'm not going to tell you which one, but one of these two breakers will trip, even though it's not rated for it.
And will that fry, or is it acceptable for the smaller one to fry in this process, or is that considered, is it supposed to stay?
It will stay. You'll be able to well, I guess let me rephrase that. There's a good chance that it'll stay in one. It'll stay together, and it may be usable. It will stay in one piece. Something will trip, and it will stay in one piece. And UL has got some requirements, and I don't know those off the top of my head, but it ties to, I think, the magnitude of the fault, where it says you can put it twice or 3 times. But obviously, the life of the circuit breaker is going to depend on how many faults and the magnitude of faults it sees. So no matter which circuit breaker you have, if every day it trips on overload, your circuit breaker is going to wear out over, let's say, a year. If it trips once at 65,000 amps, you may be able to reset it and it works fine, or it may have crossed that point. And somewhere in between is 3 trips at 20,000 amps. So there's an unproven magical line that I don't think can really be documented other than what UL tells us to test to. So we always say, if you got a breaker and you know it's seen a catastrophic fault, we always recommend, I think UL and even NEMA recommend, test the breaker or replace the breaker. You know, just to make sure it still works. You don't put it into service and it's not working anymore. Even though it looks like it's in one piece, it may be something wrong on the inside. Okay, so series ratings, just to summarize these points, are tested combinations consisting of breakers or fusible devices. We can have a fuse upstream and feeder breakers downstream. Upstream device will have a higher rating than the downstream device. The combination is the series rating. So a combination rating is what they call the series ratings, and those are all published. The upstream device may be mounted inside the panel board as a main breaker, or you could actually have a main lug only panel and series rate with the upstream switchboard feeder breaker feeding that panel. That is acceptable. So, you know, this is the way most people will do it, but this is also very good. And if you talk about cost-effective ways, you don't even have a main breaker here, and you're series rated, you're taking full advantage of cost savings. And I think this is the one, yep. Why would you ever use series rated versus fully rated? Most engineers, they use fully rated. That's all they'll do. They just know that if they're signing their name to a document, they don't want the value engineering saving of series rated. They want the fully rated, and just don't trust the UL tested combinations, and that's fine. But if you're looking for cost-effective alternatives and you need to find $1 million in cost savings, or the project's going to go under and you're not even going to build nothing, one of the ways you can do is look at the panel boards and look at series rating. As an example, I got 225 amp main breaker, which is this size here, 65K. This is pretty much the example we touched on. 120, 208 volt with an assortment of feeder breakers. We've got fully rated and series rated, priced out in different panel board styles. Both breakers will have the same 65, or both panels will have the same 65 kA breaker, same price. And using the full 65K feeder breakers, I add up to just shy of $10,000 list price. And if I use these BAB 10,000 amp rated breakers, notice they're a fraction of the cost, And adding up the price, you're around $5,000, so you're roughly half the price for series rated versus fully rated. Now, I'll give you, this is what they call a very good example. So you're not always going to be half the price to go series rated, but you know, it's good to note it's always something to look at, to keep in mind if it's acceptable to the engineer and if cost is a consideration.
If you use these combinations, and if you do replacement, you must stick with the same setup, correct?
Yep, as my setup man says, these are UL listed combinations, and this book comes in every panel board. So if you have a series rated panel board, that panel board will be labeled as series rated, and this book or something similar from our other guys will list the feeder breakers that are acceptable to be put in. And you know, that's actually probably one of the biggest concerns I hear on why engineers try and shy away from series rating, because you can install it great and everything works perfect today. 10 years from now, when everybody who worked there is gone and a new contractor comes in and he's adding a circuit, and he's been doing it for 50 years, so you can't tell him what to do. He'll look at there and I need to put this breaker in here, and he'll put a circuit breaker in. And believe it or not, these two breakers can be actually both rated 65K or 10K, depending on what panel it goes in, and you know, obviously the catalog number is different, but they will both look similar. So he may look at it and say, hey, I can just put in one of these. I got one in my truck. And that's the concern, that, you know, it is susceptible to a misapplication if not properly followed. And that's why labeling and the series rating booklet in each of the series rated panels is, well, required by UL and mandated. So then looking at our specific panel boards, you can just see, this is just a quick snapshot here of why we have so many different panel boards. From the 1 to the 5, I'm going to ignore the 5 throughout our discussion. They call it a 5P, which is an actual plug-on breaker. All these other panel boards that we have are bolt-on breakers. And you'll even see things that are called plug-on breakers. This one here is a plug-on breaker. In reality, we don't sell plug-on breakers for panel boards. If you think about safety or longevity, and you think about a plug-on breaker where you're conducting current through something that you're plugging on, you really don't want a whole lot of amps flowing through something like that. A bolted connection is always going to be inherently safer, run cooler, be able to handle more amps. But we came out with this plug-on breaker down here, 5P, which is just a big panel, kind of for the industrial application. Now the key is, in a lot of industrial facilities like to change their process up and keep things running while they're doing it, and there's another manufacturer or two out there who came out with a panel board that a lot of people talk about, getting this plug-on panel board that you can keep all your processes going, take a new branch breaker, keep everything hot, plug it in, and hook up your new process without shutting anything down. Well, that's fine and great, but if you read the instructional manual in this manufacturer's literature, as well as ours, we will explicitly tell you, do not insert these panel boards hot. So now with OSHA regulations and safety and everybody following these, it kind of takes the whole advantage of a plug-on panel board is kind of shot, because most companies now won't let you plug things on hot in this situation. Some will, but most won't. So with that said, the 1 through 4 are the most common one. 1 and 2 are very similar, lighting and receptacle type panels, and then you get up into the 4s, which are the power distribution panels. Difference being you jump up to a 600 volt rating. Your amperage ratings go from 400 amp to the small ones up to 1200 amp for the large ones. And you can see your branch circuit breakers also go from 100 amps maximum on the low ones to 1200 amp maximum on the larger ones. With that, we talked about the cables. Again, we design the ampacity of cables. We design our panel boards basically to fit the cables that should be pulled to match the size. 100 amp panel, 100 amp cables. 600 amp panel, 600 amp cables. So when you're doing a design or whether from an engineer or an install, it's always important to double check that the cables you're pulling and the cables you want to use match a panel board main lug or main breaker that's available. Sometimes you want to oversize it, or maybe you had 4 cables per phase in one application and you're replacing the panel board and that one only takes 3 cables per phase, and that's just a bunch of different things that come into play, and it's sometimes overlooked, but just know it should always be considered. So your 1A, Powerline 1A panels, again, these are 240 volt panels, 400 amp maximum. They look pretty much just like this. Your breakers, your bolt-on breakers, are your BAB, which is just like these. And you can stack them up one on top of the other. What it looks like installed is your chassis here inside your box, and then you will install a ground bar in one gutter and a neutral bar in the other gutter. One of the options that you can put in lighting and receptacle panels, as well as any panel boards for that matter, is the surge protective device. The SPD series is our new one. Now, I've got the old one here. This is the Clipper series. So about a year and a half ago, maybe actually a year ago, went into effect. UL changed they changed all their test requirements, and as part of their whole change, used to be called TVSS, transient voltage surge suppression, they threw that whole category out and called it SPDs, or surge protective devices. What the SPD does is it absorbs the transient overvoltage and shunts the extra energy to ground. So the real world example, there's 2 ways that transient overvoltages occur. One is coming from outside the building. Think about a lightning strike on the roof of your neighbor or on the power lines running down the street. If lightning hits that, it's going to travel down the conductors pretty quickly. I mean, that's a great current carrying path for lightning. So it's going to follow those conductors, and odds are something's going to hit your facility. And the largest lightning strike ever recorded is 200,000 amps. I don't think you'll get that necessarily unless you're standing on the roof, but I'm sure there's been larger but never recorded. But when you start to get into the building, that's kind of the range you're looking at. And this thing will be built to handle whatever it's rated for. And in panel boards, you can go up to 200K, and you can go up to 500 or 600 even in larger switchboards. But all that the rating means, they call them surge current ratings. All that means is how much can I withstand. Okay, the lightning surge, I'll call that the Mike Tyson. The one hit, you could be out. And if this thing absorbs the lightning strike, shunts it all to ground, and fails, it does its job. I mean, that's what it's there to do, to save everything else. The other transient overvoltage source is coming from the inside of the building. Now, from the inside of the building, they can be just as damaging as the transient coming from the outside of the building, just in a much different way. So from the inside of the building, things like Xerox copy machine. I'm sure there's some kind of fax printer or copier somewhere over here. And all these electronics, anything with solid state now, switching. Every time you switch little solid state resistors and things like that, you send little transient overvoltages across your system. And if you're sending transient overvoltages throughout your distribution system, they go wherever. So if you do something on the other end of this hallway it gets into the electrical system. It could go up to the switchboard, back down to the switchboard, and you could be seeing it in your computers right now. And of course, what are some of the most what gets most damaged by transient overvoltages?
Our laptops.
If you got a process like a PLC, those can get damaged, and all of a sudden you're running a process with $1 million batches of chemicals you're mixing. Your transient overvoltage takes your PLC out, shuts down your process, caused by the Xerox machine, and you have to dump $1 million worth of scrap because you weren't smart enough to put in a $2,000 unit like this. Now they can go to a couple of different locations, or a $20 surge strip device, which I'm not sure these are here, but
No, they're not.
you probably got one at home. We don't have them in our office either. You go to Best Buy or Target or whatever, and you buy them off the rack, and it's just like the extension cord with the 3 plug-ins on the end, and then they'll have a surge protective built in. If you buy a big screen TV today, and you actually take the time to read the warranty and the small print, if you read that, most of them are going to tell you if your $2,000 TV is not plugged into an authorized surge protector, you're out of luck. We ain't paying for your warranty replacement. I found that out. So the two kinds, then you've got the lightning, one hit, you could take it out, and then you've got the internal building generation, which is jabs. And I mentioned 200,000 amps coming. Maybe it's only 50,000 amps coming. It's one big shot though. On the inside of the building, maybe you're talking 1,000 and 1,500 amps or volts coming in, and it's just pounding. Just jab, 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 and after 1,000 jabs, you're probably going to hit the canvas. And those are the two ways that transient overvoltages can affect your equipment.
What type of internal device would create something of that magnitude?
Things that switch, so solid state switching devices, when they open and close, I think it's more like it's the speed that they operate. In the old days, things didn't open and close very quick. In the new days, things go very quick, and the quicker you operate a switching device, you're lopping off the current, which shoots the voltage up. Say right before you hit current 0, when you got just a little bit of current, you get a voltage spike. So one of the things that we always recommend is when you're designing, look at what your panel board is feeding and determine if it's a good place for a surge protected device. If you put it on the panel board, it protects all transient voltages from all 42 branch circuits. If anything's on one line of that, it'll funnel up to the main bus. This will shunt it off the main bus, so the next classroom over doesn't see your transient overvoltages. Mounting it right in the panel keeps it nice and clean. It's a change-outable device. Direct bus bar connection right into a panel board. One of the things for these to be effective, inside of this SPD is what they call MOVs, metal oxide varistors, which are the things that work quickly and shunt the energy to ground. For each inch of cable between your SPD device and your bus, the let-through voltage increases by about 20 volts. So if you add 20 inches of cable to feed, say instead of mounting this, here in the chassis, it's right there on the chassis with little bus connectors straight to the A, B, and C phase. you take that device and you mount it alongside of it here and run cable from the panelboard over to there, 20 inches of cable is going to increase your let through voltage by about 400 volts. And without looking at the actual numbers, you guys know if you've got a 480 volt system and your SPD is letting through the normal let through voltage is say 800 volts, and all of a sudden you increase it to 1200 volts because you got some cable in there. You can see how your protection can kind of wane. So it's always best to optimize that. And they come with a wide variety of interface, whether you want a light, a bell, a whistle, however you want to interface with that device. Powerline 2 panel boards are very similar to Powerline 1 panel boards, except the big difference is the voltage. So Powerline 1 panel board is 208 volts, Powerline 2 panel board is 480 volts. And they'll both be 400 amps, and the branch circuit breaker style is the GHB or GHQ. Looks the same. Same type of breakers. Both breakers will look about like this, but one will be 480 rated and the other will be 208 volt rated. Powerline 3 panel boards. This is kind of the hybrid. I talked about Powerline 1 and 2s being lighting and receptacle panels. Powerline 3s are kind of a hybrid between lighting and receptacle and a power distribution panel. The voltage rating jumps up to 600 volts, which ain't really going to be used, but it gives you a lot more flexibility on the voltages you want to use, or DC even. And it goes up to 800 amps for main lugs or 600 amps for a main breaker. And the big key here is you can also get the 225 amp max circuit breakers. So before I was limited to 100 amps, Powerline 3 gives me up to 225 amps. And what that can look like, or the benefits of something like this, you can see here's what the actual panel chassis looks like, much different than the first two. Still got a main breaker, could be main lugs out there. This design, we actually have a neutral mounted in the middle, but we'll probably see that change here in the next couple of years from our standpoint. But down here is your chassis, where your feeder breakers are. Now you can see at the bottom are the same breakers that you have on your Powerline 1 or 2. So if I got an application where I need 20 of these things, but I don't want to put in big breakers, I want the cost-effective ones, so I can put in one panel board with, say, 20 of these cost-effective breakers, but I got 3 225 amp loads that I also want to feed. Maybe I've got 3 225 amp downstream panels I want to incorporate. So now I can mount this 225 amp breaker right next to it on the same chassis. So it's a combination power distribution panel, lighting and receptacle panel. Therefore, it's a more cost-effective way where I'm only installing one panel for both needs. Now the Powerline 4 panel boards are our true power distribution panel boards. You can see just by looking at it, it looks a little bit bigger. Everything else was a wall-mounted panel board. This one, Powerline 4 family, it's still defined as a wall-mounted device, but you can see it actually sits on the floor. I'll call it rests on the floor because you'll have to set this on the floor or rest it on the floor, but you still need to bolt the can to the wall. So the 1s and the 2s and the 3s are all about 6 inches deep. Powerline 4s are about 11.5 inches deep. These the minimum height of a Powerline 4 is 57 inches, and it goes up to 90 inches high. It gives you all the way up to 1200 amps capability for main breaker, main lug, and the key here is also the branch breakers. So I can put a 1200 amp main breaker and 2 1200 amp branch breakers if I want in the panel board design. And notice in this picture, they actually have a smaller chassis as well. So they've got like power line 1 breakers in here as well as power distribution feeder breakers. And here's what the family looks like up through 1200 amp. Basically, these are all molded case circuit breakers. This is a molded case circuit breaker, but it could also be called a miniature circuit breaker or some other lines. But when we talk molded case circuit breakers, this is often what people envision, the larger breaker. Okay, the last one, first one I showed you was the power line, was called the 4B. I think it was called the 4B. Yeah, 4B. Okay, this one's called the 4F. And what would be the difference? Breaker for B, fusible for F. Panelboard is exactly the same, no difference. You can see from the front, you've got these, instead of a breaker handle coming through, you've got a switch handle. So when I talk fuses, it's always switching fuses. There's blades that go in and out with fuses in there for protection. Because you got switch and fuses, the size is going to be notably different. Same ratings across the board up here. Okay, just to give you a shot at the size here. One comment. No, we don't supply fuses. Manufacturers of distribution equipment don't supply fuses, so you'll get just the switch assembly. In a construction project, we sell all our products through distribution. So a distributor would buy the distribution panel boards from Eaton, and then they would go to Bussman and buy the fuses, and they may package it to a contractor. But you know, that's one of the differences, that there is extra steps required. People always think also as far as cost, well, I'm going to use fuses, this design, because it's cheaper. You know, it may be cheaper on the front end, but I always say after you buy your initial set of fuses, and after you buy your spare set of fuses, and then after you buy the other set of fuses because your contractor blew a whole bunch of fuses, or you know, during the first year of operation when you're learning your facility, you blow a whole bunch more fuses, or you change a process, all of a sudden all that cost savings got eaten up. The other way there's going to be differences is in footprint. If you look at these fuses, this one's probably a I'll say this one's a 200 and a 400 and a 600 stacked up there. And side by side, you can put 200 amp switches side by side. This is 200 amp switches. This is two 225 amp circuit breakers. And the bigger you get, this is the 400 amp circuit breaker, and the 400 amp switch was probably this high. So a lot of times people measure the cost with footprint. Real estate guys, developers, everything's associated to the cost per square foot. If I got a building and I've got a cost of $400 per square foot, that means if I have to take up 2 extra sections of panel board because I'm using fuses instead of a breaker, I'm costing myself 400 times, 2 feet here by 6 feet there. You can do the math and you can figure out there's a cost associated, not just in material, but in the cost of using available footage for an extra panel board section. It all comes down to how much physically we can fit into a power distribution panel. No NEC requirements or anything. It's how much stuff can I get into this panel. And just to point this out without having to talk about this one too much is we measure everything in X space. X space, it was invented, I don't know how many years ago, but 1X equals 1 3/8 inch. What it comes down to is on a normal circuit breaker, one pole is 1 3/8 inch. So 1, 2, 3 poles is 1x, 2x, 3x. So it translates trying to go, okay, I've got a breaker that's 4 3/8 inch high, and how many of those can I fit in the panel board? It's a way to translate that to, okay, I've got 26x worth of panel with breakers. How much can I fit in here? 50x. Everything works. So that's the gist behind that. Also, just to point out, you can put energy sentinels, which are just monitoring. Basically, you put any kind of sub-monitoring devices. Big today with energy monitoring, whether it's retail or a mall or a commercial building, where you can monitor the individual energy usage by all your different tenants. And just by putting in an energy monitoring program, even if you don't turn the switch on, if you put in an energy monitoring program and say to your tenants, we're monitoring your energy, and I won't say tenants I'll say like a corporation, where each department in the facility has their own energy responsibility. You can just tell them, we're monitoring your energy, and you'll be billed accordingly, and see how much energy we can save. Just by telling them that, your energy usage will drop by on average 10%. Without even turning the button on and measuring anything. It just translates into real world efficiencies. People use more sense. In addition to that, and this applies to the switchboards as well, but you can put in different energy displays, whether you want to read the information right at the panel board with a clipboard and a piece of paper, or everything today now can be put on the internet. So we can put in a little box. It is a built-in web server that you can then pull up at any PC you want authorized, to pull up a screen and look at your energy usage information, or send it to a building management system. All that is available today.
Do you have anything that does that at the circuit level or strictly at the main?
That's a good question. We don't have anything that monitors directly at the circuit level for 20 amp type circuits. We have it at the circuit level for the 3-pole breakers. So, 100 amp circuits is kind of what I would say. And usually that's dictated by cost effectiveness. If you're going to spend $500 on a point to measure a 20 amp breaker, and you can run that breaker for 100 years, and no matter how much monitoring you do, you'll never be able to save $500 in energy. So we kind of looked at it that way. But for data centers, we do have a division that deals with data centers, and their individual circuit loads are a lot more important because they use them in entire facility interaction, and they've got an actual purpose on there. So there is products out there, which we make too, for data centers, that go down to the individual circuitry. It gets kind of expensive.
Yeah. Would that be in this type of catalog, or that's only this one?
Yeah, that would not be in that catalog. It would be under our Power division.
Power?
Yeah, Power, our UPS division. And I believe they call those RPP panels, or similar. When you put in a UPS system for a server, you'll have like a PDU, power distribution unit, that converts that, and then on the load side of that, you'll have the ability to put in that branch monitor. All right, so switchboard sim, probably got less than a half hour left.
Good.
Okay. Switchboards are big panel boards. Simplified a little bit, but basically this is your power distribution panel board, which is tops out at 1200 amps. A switchboard has the ability to go all the way up to 6000 amps. And your panel boards were your wall hanging devices, or at least wall supported devices. Your switchboards are floor mounted devices. So from an installation standpoint, that's the biggest difference. Switchboards are really consisted then of a framework structure, 4 posts, framework all the way around the top and the bottom. You can see right here, here, and here, horizontal bus. Okay, so that's your A, B, and C phase. And what that gives you is the ability to stack multiple structures side by side. So you can put in one main device, put some feeders on the same type of panel board. You'll have a vertical busing in there. Main device with some feeders, and just keep adding sections and sections and sections until you get everything put together. Getting the hang of this. Some of the other, sorry.
Are all horizontal bus though? For switch gears?
And I'm going to circle back to that, switchboards, because there is a difference between switchboards and switch gear.
If they are all horizontal.
90% of the time, 95%. They all have that capability, but in the instance where you've got, you're above the 1200 amp, so maybe you've got 1600 amp, and all you've got is you want to have one breaker. Cable in, cable out, one breaker. You don't need the horizontal bus because you can fit everything you want in one structure. So there are instances where you build a switchboard and you don't need the horizontal bus, but most of them do. So I mentioned they're freestanding, they sit on the floor. They can be front or rear accessible. Most commonly, people try and mount them against the wall, again, if you're saving footprint, because you don't need any rear access. But on certain devices or certain layouts, you want to put it in the middle of the room. It allows you to get around to the back, helps with your cabling or what have you. So it's got the 6,000 amp main bus. Right now, 5,000 amp is the maximum main device, main breaker, etc. Has capabilities for utility metering, customer metering, circuit breakers, fuses, and it is actually UL 891 is the standard for switch boards. And the way it physically looks is this will be your main structure. So you can have some metering at the top, and these, of course, is the old analog meters, which nobody uses analog. Everybody uses digital meters now. Utility metering compartment stuck in the middle, where utility can come in and put in their CTs. A main device here, which then feeds the horizontal bus that would run behind this distribution section. So there would be a vertical bus tied into the horizontal bus that feeds all these breakers. Notice they're not, they're different depths. So this one, because it's got a big breaker, may need to be 30 inches deep. This one, because it's only got smaller breakers, maybe it only needs to be 18 inches deep. It's common practice to front and rear line them. It's not mandatory, but it's got a little more aesthetic appeal, I guess. So for the main devices, just like panel boards, we had main lugs only, fusible switches, or molded case breakers. Because we've gone higher in ampacity, fusible switches, we've got a new kind of fusible switch called a bolted pressure switch. A normal fusible switch goes up to 1200 amps. A bolted pressure switch goes up to 4000 amps. The bolted pressure switch is it just takes a lot more beef or a lot more pressure to hold things together at that amperage. And two other classifications of circuit breakers are an insulated case or an air power circuit breaker. Molded case breakers go up to 2,500 amps. So a molded case breaker, the biggest one might be, say the width of this computer and, maybe 20 inches high. That'd be a 2,500 amp one. And higher than that, you need to look at other alternatives, which is where the air power circuit breaker comes in. Well, just to step onto this is the another shot of the bolted pressure switches. So you can have a manually operated bolted pressure switch or a electrically operated bolted pressure switch. When we talk about service entrance, it's going to require ground fault. So if you get ground fault required, you get an electrical operated switch. But the other circuit breaker options are the Magnum DS or Magnum SB circuit breakers. Magnum DS is a air power circuit breaker that meets UL 1558, which is designed to be installed in switch gear. Magnum SB is can't think of the number, but it's the same standard as molded case circuit breakers. 489 maybe? Not checking. But it's the same standard as molded case circuit breakers. And there are different standards in testing. But the molded case circuit breaker standard is designed to be installed in switchboards. So when you're talking a switchboard with molded case circuit breaker feeders, you would more than likely use a Magnum SB insulated case circuit breaker. The primary difference between a switchboard and switch gear is a switchboard is rated, tested to only 3 cycles. When UL comes in with their standards, there'll be different testing requirements that UL will put on switchboards and switch gear. Switchboards, recall that picture, everything's open. There's no barriers, or there doesn't need to be any barriers between anything, so it's much more cost effective. So the circuit breakers, the molded case circuit breakers, could be stacked up one on top of each other. So if one circuit breaker blows up, you're probably going to take out the circuit breakers next to it in some regards or another. And the busing or the bracing itself is designed to handle 5 cycles of fault current without something tripping. And switch gear provides the different, more robust design when it comes to the cycles. Switch gear can handle 30 cycles of withstand. In addition to being barriered and compartmented, amongst each circuit breaker is individually barriered and compartmented. The busing, the horizontal busing, is individually barriered and compartmented, and the cable compartment is barriered and compartmented. So all these different things keep any faults isolated as best as possible to the location of the fault without taking down everything next to it or greatly lessening the chance of taking down something next to it. So the switch gear is designed to withstand 30 cycles of fault currents. Switch gear feeding a switchboard, for example, as a load. Switch gear breaker would use a Magnum DS. The Magnum DS breaker is tested to withstand 30 cycles. Going harken back to the early slides about the withstand, it can sit there, let the full fault current flow through it while it delays, while it looks downstream, and what lets something downstream be the one that trips. As a common rule, you always want your circuit breaker closest to the fault to be the one that trips. Just from common sense or practicality, if you have a choice, if I have a fault here and I got a choice about shutting down the power to this room, to this floor, to this building, or to this block, I'm probably going to choose this room. It's not always feasible, but you know, that's what you always prefer. So switchgear has the benefit of sitting there, letting things downstream trip if possible, and if they don't trip, then it trips. So Magnum SB is the switchboard breaker, which is designed then only for a 3-cycle switchboard, and therefore it's not designed to sit there for 30 cycles. What are the trade-offs, or what are the benefits? It's a little better, it's more cost-effective. You know, you're not going to misapply it because you're not going to put a device that sits there for 30 cycles into a switchboard that would blow up in 30 cycles. So, now, there's nothing preventing you from putting, you know, the DS in the circuit breaker in a switchboard. We do it commonly, just it's got to be done under the right application. They also have the ability to do draw or fixed on those breakers, on the Magnums. So while you can chassis mount a main device, you know, just like on a power distribution panel, most switchboards are going to be individually mounted. So they'll mount the main breaker somewhere in the structure and take up a third to a half of the structure. We're kind of moving away from this. Excel used to put metering compartments inside switchboards, inside buildings, and they've moved to the point now where they want those CTs and metering outside. So you'll put the switchboard in, and they're directing more and more where you'll put a separate set of CTs outside. You know, it's an Excel thing, so you may see different utilities do different things, and I don't think it's necessarily a rule yet. It's just a guideline that they're pushing. So if you did want a meter, put a utility meter thing, and this is about what it looked like. This compartment here is blown up, and basically it just looks like copper links here in between all those phases. So Excel, for example, would send out CTs to the contractor. He'd pull out these 3 copper links and put CTs in there. Each CT would have a lead that would then run to a utility wire to look just like this up here at the top. Bar type CTs. You'd run the wires to a watt-hour meter that you maybe mount on the side of the building or what have you. And you know, one of the verbiage you'll hear is hot sequence and cold sequence, and what the heck do they mean for utility metering compartments? If the utility metering compartment is on the line side of the main breaker, it's called a hot sequence, because whether that breaker is open or closed, that utility compartment is always hot. If you swap those and put the main ahead of the utility compartment, it's called a cold sequence, because if you open that main, then that utility compartment is cold or dead. This doesn't fly anywhere up here, not in this neighborhood. This is what Excel looks for. The hot. Yep.
Juice anybody that's messing with it?
Yeah. And part of that requirement also is this. There's a door over there, whether it's a half structure or whatever. Once the thing gets installed, utility will put their padlock on that door with their key. So a great way to borrow energy from the energy company is to figure out how to get in there and tap off ahead of where that meter is. So that's why they like to keep this at the front versus this, because it's easier if the customer has access to the main breaker. It's very easy to put a little CPT on there or some other means to get that no-cost power, which of course is frowned upon. But as I mentioned again, this is the way they're doing it, and then Excel now is kind of taking this part out of the switchboard and putting it outside in a separate cabinet. What you have to do with the drive-by, you know, they've got the radio type deals that they do all their wireless metering, part of the smart grid now.
But are they taking the CT cabinet out or just the meter out?
CT cabinet.
So you have to have a termination box outside?
Yep. Yep.
Oh, okay.
And
Or a 4,000 amp switch gear, that would be a big termination box. You bring the
Yep.
cables in and out.
Yep.
Wow.
Yep, that's exactly what it is. But you know, must make it easier for them. I'm sure it makes it easier for them because they're definitely pushing that way. We're probably doing more that way than inside the switchboard. And 2 years ago, it was just the opposite. Okay, that was utility metering. Now, the other thing that, you know, if I'm dealing with you at our company, I'm not going to let you design a switchboard without some type of customer metering or user metering. So when it hits the site, contractor installs it, everybody leaves, the owner's taken over, and he doesn't know what electricity hardly is. This meter gives all the information he needs, and you can make low cost, low information meters to high cost, high functionality meters, but utility's giving you power, and they're billing you. And unless you've got a meter on, then you're sitting back and you're trusting that a utility must know what they're doing because they're billing me every month. I'm paying it and everybody's happy. Well, sometimes utilities make mistakes. And if you can catch them by putting in a $3,000 meter, find out they made a $50,000 error on the power factor penalty they were billing you on, well, you could pay for that and the company Christmas party. The other things are like facility expansion. If you want to add load to your existing facility in a couple of years, you always have to understand where your facility is today. So the kind of old adage is you can't manage your energy unless you can monitor it. For the customer metering, they put CTs. We factory install those just right around the bus, maybe on the line side of the breaker or wherever that actually makes sense on the load side of the main breaker. And this isn't actually, we don't make that meter anymore, but you can go, just to point out, you can go with a very low cost ammeter, voltmeter, just give me some basic information. These are pretty much obsolete nowadays. You can get a very low cost effective meter, I'll call it a mid-range one, that does voltage, current, frequency, power factor, watts, and watt hours are three of the key pieces of information that when you're looking at energy monitoring, that can give you a lot of good information at a pretty reasonable price now. Likewise, you can kick it up a notch into what I would call a power quality meter. There's energy meters, power quality meters. Power quality meters will give you all the energy information, the amps, the volts, the watts, the watt hours, etc. But it gives you also information on power quality. Things like harmonic distortion, things like K factor, or waveforms, graphic waveform display. So on the front of this unit, and this is an older one too, but nowadays on the front of a meter itself, you can actually look at a waveform, see what it looks like. All these meters today now have the capability, not these meters, but our new meter family has the capability to have embedded web servers or Ethernet communication like Modbus, TCP, IP, or what have you. And if you're designing a building from scratch, you put your customer meter in there. All you basically need to do is put a LAN or some kind of Ethernet jack in the electrical equipment room, and you can tap right into the meter. And if you don't want a computer web server where you can pull up the page and everything right there from the meter, at least you can get it very cost effectively into your building management system, just to pull out data points like watts or watt hours in your building management system without having to do really any infrastructure except for a cord from the wall to the meter. And that is the trend of the future. People have started that over the last couple of years. It's almost become the de facto standard. Distribution sections of switchboards are really the same as the Powerline 4 panel boards. It does have the capability to go to a lot higher amperage, but the design and the construction is the same. Breakers mounted upon breakers. They're called group mounted. Group mounted is basically just stacked on top of the other. When I talked about if one fails, you're going to blow, possibly blow down on the next one. All switchboards are building blocks on a distribution section other than the main. You may have larger than 1200 amp breakers. So the chassis can hold a 1200 amp molded case breaker, but if you get to a bigger breaker, like if I got a 4000 amp main and I've got two 2000 amp feeders, there's different ways you can do that, different options of mounting one on top of the other or what have you to get that configuration done. Same rule applies on the SPDs or the TVSSs. Every switchboard that goes out today, just like customer meter, there's too much of a value in there not to get it. The same thing applies towards the SPD. If you put in a switchboard and you're getting a service entrance, you're coming in from outside into your facility, it's just a, it'd be foolhardy not to put in an SPD for a few $1,000 investment insurance policy on a $1 million building. Same type of energy metering devices, sub-energies. And we're going to touch just on service entrance a little bit. If you got a building wall here, here's one that shows utility metering outside. Break through the building wall, and you've got your switchboard here. And this switchboard is classified as a service entrance switchboard because it's got a main service disconnect. It's the point where, let's see, it's the point where the service entrance equipment must be located near the point where the supply conductors enter the building. You got a couple of different configurations. A service entrance switchboard can be main lug only, but you would be limited to maximum of 6 disconnects to de-energize the entire building. Or you would have to have one main breaker. The majority of people choose one main breaker, but there are instances where rather than a main with 6 feeders, eliminate the main and just use the 6 feeders, and that could save you some money. And what's the concept behind this? And why is it service entrance labeled? Because you build a commercial building, you'll have a talk with the fire department. He'll come in and he'll know, he'll look at your facility and give you the stamp of approval or whatever they do, and they'll make sure when he comes in and there's a fire going on and he needs to disconnect power, they need to know, I need to go to this board, it's labeled as service entrance, and I turn off my 1 disconnect or I turn off my 6 disconnects. And you can imagine the trouble if all of a sudden they had to turn off 10 or 20 disconnects to turn power off for the building. So that's kind of how this kind of evolved here. There's a bond between the neutral and the ground that is part of the service entrance requirement. Think about that. Keeping the neutral and the ground bonded inside prevents stuff from flowing back out to the transformer on the neutral. Transformer being owned by the utility. I mentioned the service entrance must be factory attached to the panel. If had this come up, ship a switchboard or a panelboard out to the field, no service entrance label. Inspector fails it, and how do you get a service entrance label on there? It's not allowed to be done. You can't walk out there with a sticker and throw it on. It has to be done in the plant. Now, there's been push to shove where there's ways where you can have the plant guy or some authorized worker come out, meet the UL guy out there, and UL guys are about $5,000 for a 3-hour visit or something like that, and reconstruct it in his witness. Put the sticker on in front of him, and he may bless that, but you better have a reason to do that. Ground fault protection. The one thing about service entrance, it's actually going to filter into how you're designing your switchboard is every switchboard or every service entrance rated 1,000 amps or higher at 482.77 requires ground fault on that main breaker, or if you got the 6 disconnect rule, on all 6 of those breakers. And that is I don't believe there are any exceptions on that one. So this is what it looks like with one main or 6 feeders.
Now, are you saying that it's just the device itself or the breaker supplies?
Ground fault protection has to be there. It could be separate or in the breaker.
It's for touching the breaker, right? So not downstream.
It's for downstream, yeah. Yeah, actually I've got a picture here on that may answer your question here. But if you got a 2,000 amp breaker here and you get a ground fault anywhere on the load, so you could be down 2 levels of breakers even. Ground fault inherently is going to have a high resistance because it's not following a bus bar, it's not following a wire, it's finding some other way to escape from the cable. So it's going to inherently have a lower fault current value. In this case, 2,000 amp breaker, you've got a 300 amp ground fault, and that'll keep running and running and running.
Oh, okay, so but it's not the same as a human protective ground fault at 6 milliamps at below.
Correct. Much different. In fact, I think this is too low. Typically, a 2,000 amp, you'd probably set it up as 500 or 1,000 amps ground fault protection. That's the type. Yeah, there's 5 milliamp and 30 milliamp ground fault protectors that, for example, you'd have at your home, in your spa, or in your bathroom.
This is a full fault.
Yeah, same concept, but bigger. So that's why you have to have special ground fault protection, because your currents are going to be much less. 2 basic ways to do it are zero sequence and residual. Zero sequence takes 1 CT and you run all 4 wires through, A, B, and C neutral through it. Or residual has 1 CT on each of the phases, 1 on A, 1 on B, 1 on C, 1 on neutral. And that's how circuit breakers do it. So the zero sequence, you got the CT around, and it's always going to look at current. At any snapshot in time, you got alternating current, you got current going in, current going out, in 2 different directions. It looks at that vectors, and at every snapshot in time, that current should be 0. Current going this way and this way will cancel each other out. Okay, so that should always be 0. If it's not 0, if you get a ground fault here, you're going to get some value measured here that is going to be equal to the ground fault current. You'll send that to a ground fault relay. Once that determines you've hit a ground fault value to trip, you'll connect to the main breaker and shunt trip the main breaker. Now, why we use this method in breakers, the residual method, which is around each individual CT, goes back to this relay. The relay is the one that sums up the vectors. And then the relay can then go to a main device shunt trip. The reason is because all that is built right into the circuit breaker. So this frame here is your circuit breaker. All your CTs and everything, you don't have to do anything extra inside the circuit breaker. The shunt trip is built into the circuit breaker. The only thing extra you'd have to do is wire if there's a neutral, wire a neutral CT, which we provide with it. You just got to run your cable through there. So you can see, to do it with a circuit breaker, it's almost doing nothing. We talked about the different switchboard construction, can just have a bunch of different configurations. Switchboards are custom assemblies. I don't think there's a such thing as any 2 switchboards that are the same, unless it's the same job. There's different building blocks and stuff. And one more thing I wanted to mention on switchboards. We talked about cables this whole time, and I don't think you've talked about busway yet, probably.
Next time.
Next time. Busway is instead of cables feeding your switchboard, And I won't think about it from the utility, but say you've got one main switchboard, a 4,000 amp main switchboard, and you're feeding two 2,000 amp distribution switchboards. It's rather than cables, when you're talking 2,000 amps, for example, you are talking, what, 6 cables per phase, 3 phases and a neutral, 24 cables that you've got to use a cable management system to get all that feeding up through raceway or through pipes, conduits, whatever you want to do. Busway takes copper bus bars, just like the horizontal bus in a switchboard, sandwiches together A, B, C neutral. And rather than use 6 per phase for cables, you can just use one busway that might be 5 inches by 9 inches that runs from the switchboard, the main switchboard, downstream to the 2,000 amp switchboard. And it can be very cost effective to do it that way. And here's kind of what it looks like. So just to make panel boards have to be cables. But switchboards have the ability for a busway connection, and that's really just the takeaway on this. Here's kind of visually what we're looking at. This is a busway up top, and you can see the lines here, the copper bars coming out. So when the busway is running across the ceiling, they're all sandwiched together. When you come, down into the switchboard, they spread out and create, follow the air clearances that are required inside the switchboard. So you can bolt it, and it's a bolted connection right on. That's it for that. We touched on switchboard, switch gear differences briefly. Could talk more about that if you'd like, or I also just wanted to bring up consulting application guide. We've got the new ones. I'll talk to you about getting some of the new ones in your hands. It looks the same, but it's got a couple of different chapters and some new information and all the updates that happened since 2006. So we'll get some of those into your hand, but this is a great resource. We came out with this consulting application guide like, 30 years ago now, and it is kind of evolved into the #1 resource for consulting engineers across the country as far as I need information to lay out stuff. I don't need pricing, and that kind of stuff. I need footprints, I need weights, I need heat loss, I need technical details, control power requirements, that kind of stuff. And all that is in here. And it's broken down simply into we've got a whole chapter at the beginning, which is like electrical engineering refresher 101. It's about, I think we're up to 40, 50 pages now of a few pages on generators, a few pages on UPSs, a few pages on ground fault, a few pages on short circuit. So I go to that all the time. Great refresher. Then we've got sections on medium voltage equipment. We've got sections on we'll call low voltage equipment, which is 600 volts and below. We've got sections on control equipment, motor control, motor starters, VFDs. We've got sections on, I'll call metering and relays and software. So all the communication aspects. I may have a switchboard or a switch gear, but what you're doing as far as the metering, the software, and the relaying is kind of the gold plating on the switchboard. The switchboard is the function, and the metering and all that are the features that you want with that function.
You make meters as well, or the kind of a...
Yes. Yep. We and those pictures were bad on there, but in 2005 we came out with our brand new software and hardware architecture called the Power Expert architecture. Power Expert architecture was the we kind of led the industry into the I'll call it the Ethernet based high volume meters. We've got memory chips in there which are on the order of, I think, 2 gigabytes to 8 gigabytes, and there's still meters out there today which you buy with a memory chip of 256 megabytes as the biggest you can get. So all the extra memory, it's just like computers, you know, and we came out with this architecture from the ground up. We spent a lot of money designing it, trying to get the cutting edge, and in 5 years, could change again. But as of today, it's pretty darn good technology. Any other questions? I guess I don't want to keep you here through lunch, but I'm answer questions if you guys want to talk about anything related to power or the industry, even for that matter.
And the PowerPoint presentation will be online, right? We'll get a copy of it?
Yep. Get that,
Maybe
Dave.
in the instructor folder. Just for,
I wanted to get some information regarding the data protocols for the monitoring equipment that you sell.
Okay.
Get some detail. I got technical questions regarding whether it's event-based monitoring and a bunch of other real nerdy type questions.
Okay.
What's the best way to get that?
If you wanted to just read through it yourself, to start out with and see what we had, we've got this book online, except 2011.
Okay.
And
it's in there.
yeah, let's see.
If it's, all through your website, I certainly want to.
It is through there. Chad's got a link here.
I'll send you
That
that. Here you go.
Yeah, I think he could send us, but right here is, we've got this link, in addition to all the other stuff, that you can get the consulting application guide right on your computer if you want. And that gives you all the technical details. Now, we also have a 1-800 number. It's called 1877 Eaton Care, ETNCARE. I didn't make the name. And we've got a complex out of North Carolina between some of our plants that we've got a few hundred technical resource engineers. Everybody from, that's where we train our new hires, to guys who have been working for a company for 30 years, and they're very good technical resources. So depending on what kind of question you have, almost any skill level will be able to answer that for you. And as well, you work with a contractor or a consultant?
I've been in telecommunications and
Okay.
data as it relates to telecom.
Okay.
I'm looking very interested in energy monitoring.
Okay.
If it's event-based, it might be some way to take off a 100-amp system and make it one machine do several several things. So that
Okay.
you might, as you said, $500 to say a
Yeah.
1-amp breaker it's not going to cut the mustard. But
Yeah.
if you do what's called event-based reporting, and one thing looks at lots of things.
Okay.
It's somewhat interesting to look at.
Yeah. I mean, I'm an application engineer. I work with consulting engineers primarily. But we also have an office full of, I think we're at about 17 engineers in our office now who call on a variety of people, from contractors up to industrial guys like 3M, and everybody in between. I wouldn't guess, though, you wouldn't know anybody you can call on you guys, probably. That wouldn't seem like that'd fall in there.
No, I used to write stuff that ran out. In one case, long distance fraud, where you're constantly checking to see if, for repeat patterns, if things happen, and then after long distance became more or less free or a non-issue.
Yeah.
Then it was other type of events that you watch the stuff and then you rat it out by calling them, by emailing them, by setting bells off, whatever it is that needs to happen, notification type stuff. And that's what my interest is.
Okay.
I've never done it in electrical power. It's always been data type things. But now that the electrical power is producing data, and I'm not sure anybody's. I haven't seen where that's being taken off too much at this point.
Yeah, and
Certainly at the high end of always.
yeah, I look like a data center. They'll a lot of times they'll just take our data points out of our meter and they'll bring it into their system. I won't see what they do with it, but they know what they're doing with it, and they're doing it for a reason, to keep an eye on things, and they'll have alarms go off when they break certain expected values. I'm gonna leave some business cards up here as well, so feel free to take one. You know, if you start going on the road and you need a little more help, then give me a call. I may not be able to help you. I like to say I know a lot. I know a little about a lot of stuff, but we got guys that know a lot about a little of stuff.
Any other questions, guys, for Todd? And Todd called in all the engineering firms, and I know if we have Mashad Cooley and Justin, where are you now? I forgot.
Kane Thomas. Kane Thomas.
Yep, and we have also People Electric, right?
People,
Hunt, Peoples. Where? Phil, where are you? I keep forgetting. No. Elliot.
Elliot? Okay.
Yeah, so we have
Dave
a bunch
Enright, I think, deals with you guys. Who was with Hunt? Andrew Smolsky or Jay Mikla pop over there a couple times a week. You can see those guys?
No,
Oh. You will.
of